All right, yesterday we created our inverse trig functions and we saw how to draw the basic inverse trig functions. So just when it was inverse sine x, tan x, cosine, etc. But what about if we vary it a little bit? How do we handle it? So I had to draw y equals 5 inverse sine x on 3. First thing I basically do is work out the domain and range, because I could draw the same picture for every single graph. All I've got to do is change the labels on the axes to match whatever the domain and range is. So domain, well, of the basic inverse sine one, we know that it goes in between -1 and 1. But instead of x, I've got x on 3. So my domain for this one will become in between -3 and 3. So when I draw my curve, instead of labelling -1 and 1, I'll label -3 and 3. With the range, now I've got to be careful here, because remember, that 5 is really associated with the y. So it's y on 5 is in between -pi on 2 and pi on 2. And so now I know that the range of this curve will be -5 pi on 2 to 5 pi on 2. So as I say, I'll just draw it up exactly the same as I did yesterday, but I'm just going to change the way I label the axes. And I can draw the same picture as I had yesterday. Okay. I mean, that's fine when you've only got one graph on the actual axes. Of course, this one's a little bit more interesting. Inverse tan of the square root of 3 minus x squared. All right, well, let's try and work out the domain and range. Domain first of all. Now, the domain for inverse tan, the basic one yesterday we saw, was all real x. However, there will be a restriction on this one, because I can't substitute everything into the square root of 3 minus x squared. So now that becomes what's going to determine the domain. So my domain, if I said to you, what's the domain of the square root of 3 minus x squared, because that's what's going to end up being the domain of this function, because remember, we can substitute anything into inverse tan. It's the square root of 3 minus x squared. Well, we would have said, oh, well, underneath the square root, sign's got to be greater than or equal to 0. So minus root 3 to positive root 3 will be the domain. Now to work out the range. The range was normally minus pi on 2 to pi on 2, but that's when we had the complete domain. We've got a restriction in the domain. So let's test the endpoints and see what values they are. So when I sub in root 3, I get 0. Obviously, I get the same with minus root 3 because x is squared. All right, well, I certainly know it's not going to be a flat line going from 0 to 0. But I do know, looking at this, odd or even function. Well, how do you tell if something's odd or even? Function negative x. If you substitute in negative x there, what are you going to get? The same thing. Therefore, even. All right? So I know it's going to have reflection around the y-axis. So the midpoint for this is going to be a good one to test, because that's probably going to be the other extremity of the range. So let's put the midpoint in. X equals 0 gives us pi on 3. So what does it look like? Okay. Let's draw up there. So we know that it's going up to pi on 3, minus root 3. It's 0 at root 3 and minus root 3. And then it will go up to pi on 3. It's something like that. And obviously, if you're unsure, once we know how to differentiate inverse tan, you could use calculus to check and things like that. All right, let's draw y equals the inverse sine of sine x. The temptation here is to draw the line, because inverses cancel each other out. However, it is an inverse sine function. Let's do the domain. The domain, I'm substituting into sine x. But sine x is only allowed to go between -1 and 1, because remember, the domain of the inverse sine function is -1 and 1. So what I'm substituting into, what does that do to my sine curve? Does that change anything? Sine x, well, it's always in between -1 and 1. So I can substitute anything in. So all real x is the domain. The output of the inverse sine function can only give me things between minus pi and 2 and pi and 2. So it can't be the complete line y equals x. Let's just draw this up. At least I know that bit of the curve there. There's y equals x, but I've stopped it at minus pi and 2 and pi and 2. However, it keeps going because we said the domain is all real x. So the question is, what does it do? Well, I know that at pi, I could substitute in and work out pi. Sine of pi. 0, thank you. Inverse sine of 0. So I know we're going to have an x-intercept at pi. Let's try it. Sine of 3 pi on 2. Inverse sine of negative 1. No, it's not 3 pi on 2 because inverse sine can only give answers out between minus pi on 2 and pi on 2. So let's try that again. Inverse sine of negative 1. That's right, negative pi on 2. If you're unsure, look at the graph. So what we actually get is zigzags. So it's going to zigzag all the way along the x-axis. Let's try it the other way around that. Let's try the sine of inverse sine x. So once again, you would think y equals x. Let's have a look at the domain. This time it's a sine function. Now the domain of a sine function is all real x. However, I'm substituting that all real x into inverse sine, and that I can't do. So I'm going to be dictated by the domain of inverse sine, because ultimately that's what I'm substituting into first. So if I can't substitute it into inverse sine, then I'm not going to be able to get an overall answer. So its domain will only be minus 1 to 1. Well, that means it's a restricted domain, so let's have a look at the endpoints. When x equals 1, sine of the inverse sine of 1, inverse sine of 1, pi on 2, sine of pi on 2, 1. Makes sense because we're thinking y equals x. Negative 1. Yep, sure enough we get negative 1. And just to check the middle as well, yes, 0 is 0. So this time, when I draw it, it'd be similar to the last graph, but there's a few key differences you'll notice. This one doesn't zigzag. It just has that one piece of y equals x. But the extremities are different as well, of course. The other one went from minus pi on 2 to pi on 2. This one goes 1 to minus 1. This one. All right. We shall have a go at one.